So let us start. Okay, my screen is visible? Yes?
Yes, sir.
Okay. So today we will solve first numericals. Then after that we will discuss. Okay. So today is lecture 5, right? And date is 28/22. Okay. So let us talk about. So first we will see the numericals. Okay, so to determine the depletion and inversion region, means width I am talking about, or you can say depth. To determine the depletion layer, width or depth of a p-type semiconductor, of a p-type silicon semiconductor with doping concentration of let us say 10 to the power 17. What will be the unit of doping concentration? Yes?
Per centimeter cube.
Good.
Per centimeter
Per
cube.
centimeter cube. And second, it will be 10 to the power 18 per centimeter cube. And thirdly, it will be for 10 to the power 19 per centimeter cube. So here I will solve this numerical only for the one concentration, that is 10 to the power 17 per centimeter cube, and remaining for doping concentration of 10 to the power 18 and 10 to the power 19 you have to solve at your home, and in the next class I will ask you the answer. Okay, so let us talk about what they have asked. They asked to determine the depletion and inversion region of a p-type semiconductor. So let us talk about first, that is depletion region, right? So under a strong inversion, basically under a strong inversion, if they didn't mention also you have to understand it is under a strong inversion, depletion layer. So how do you represent the depletion layer? Yes, in the last class we have already studied. I am expecting the answer from your side now. So what is the formula mathematically? What is the formula to determine the depletion layer? Yes?
Under root 4 epsilon
So
naught
first of all,
epsilon
how do you represent depletion layer? What are the symbols to represent? Yes? WM. Okay, now you can tell me the formula. Under root
4 epsilon naught epsilon r by
Okay.
na into e square
epsilon 0 epsilon naught
by na
by NA.
into e square
Okay, E square
into kt ln na by ni.
KT ln Na by Ni, right? Good. So this is the formula to determine the depletion layer, right? So here, what is given? If you see, Na is given, right? So first case we are considering, that is 10 to the power 17 per centimeter cube. E is charge of electron, right? So its value is 1.602 into 10 to the power minus 19 coulomb. Now we will talk about K. So K is Boltzmann constant, right? So here we will determine the value of K in electron volt, right? So in electron volt, Q. Oh, sorry. Yes. So this is Q or listen, Q or E, both are same charge of electron. So this is equal to 8.617 into 10 to the power minus 5 electron volt per Kelvin. Remember. So this is the value of, you have to remember, these are the constants you have to remember. This is the Boltzmann constant in electron volt, and temperature, whenever the temperature is not given, then you have to understand at room temperature. So it is 300 Kelvin. Now, what are the unknown quantity here? Anything unknown? Na is given, charge of electron we know, Boltzmann constant is given, T, that is temperature is given. What is unknown here now? Yes?
Sir, epsilon r.
Epsilon naught. Epsilon naught is very well understood. 8 point. Yes? 8.85 into 10 to the power minus 12 farad per meter. Epsilon 0. Epsilon 0, that is for what? Relative permittivity. Which type of material which material we are using here? Can you identify?
So silicon.
Silicon. So we have to write the relative permittivity of silicon. So the relative permittivity of silicon is 3.6. Or we can also check on the internet. Relative permittivity of silicon. It is 3.9. Silicon dioxide, sapphire.
I think it's
No,
11.7.
11.7. Okay. So it is 11.7.
So also we must convert epsilon naught into CGS.
Into?
CGS units. 10 raised to the
Oh,
minus
okay.
1.
Okay. So this is in per centimeter cube. Okay. So we will have to convert into the. Okay, we will also convert into the meter cube. So it will be 10 to the power per centimeter cube. So it will be 26 per meter cube. Okay. So now it is correct. Now it is correct means no need to convert the epsilon 0. Now what is unknown? Epsilon 0, epsilon r is known. Kt Na by Na. Okay. Now we will have to. Okay. So what is this value? Anyone can relate this value? So this is phi b, bulk potential, right? Which is equal to Kt ln Na by Ni, right? If you remember. So if you calculate the value of Kt ln Na by Ni, then what will be the value here? So the Kt in volts in electron volt is how much? 8.617 8.617 into 10 to the power minus 5 multiplied by T is 300 multiplied by ln Na is 10 to the power 17 by Ni, but nobody asked me what is Ni. So Ni is intrinsic carrier concentration. Intrinsic carrier concentration in centimeter per cube. So intrinsic carrier concentrations. What does it mean by? What do you mean by the intrinsic carrier concentration? Yes. It means that the number of electrons or the number of holes will be equal in case of intrinsic material. That's why I always suggest you all to revise the semiconductor. So whenever we talk about the intrinsic material, it means that in that material, the number of electrons and the number of holes will be equal. So for silicon, Ni is equal to 10 to the power 10 per centimeter cube. So it means that 10 into 10 to the power 16 per meter cube. Okay, so you have to remember at least for two materials, silicon and germanium. You have to find and you have to remember. So now you can calculate phi b. So where phi b is bulk potential, so which is equal to now 8.617 into 10 to the power minus 5 multiplied by 300 multiplied by ln. Na is 10 to the power 17, it is in centimeter, and for Ni it will be 10 to the power 10. So how much value you are getting? Can you calculate? Calculate and tell me what is the value of phi b. You all are attending the lecture from
0.419.
0.419. Very good, very good. 0.419 electron volt. The unit is electron volt. Very good. Now you have calculated the bulk potential. Okay. So as I told you, in case of semiconductor, let us talk about this is EV, this is EC, right? So here at exactly not nearly at the center, the intrinsic Fermi level exists, right? So what is the energy band gap energy of silicon? I have already discussed about it. Anyone remember the value? Yes, it is 1.1 electron volt at 300 Kelvin. Remember. So what is the value of EFI here exactly? If you calculate here, EFI is equal to just EG by 2. So which is equal to, if you divide 1.1 by 2, then what is the value of, what will be the value here? Yes? 0.55 electron volt. Okay, so what does it mean? It means that the value of phi b is less than EFI. Okay, so now you have calculated the phi b value, right? So phi b means kT ln Na by Ni. You have already calculated. So just you have to substitute this value in these equations and calculate the depletion layer width, that is Wm. So now Wm, which is equal to 2 under root F70 F7R by Na E square. Na E square multiplied by phi b, right? So now you have to calculate the value here. So just substitute all these values, that is 2 root under F70. F70 is 8.85 into 10 to the power minus 12. F70 is 11.7 divided by Na is 10 to the power. Okay, we are writing F70 in farad per meter. So we will have to convert the concentration, that is Na in per meter cube. So exactly the value of 10 to the power 70. So 10 to the power 70 means 10 to the power 23. It will be 23 here per meter cube. I will let you know how to convert from centimeter cube to meter cube. Okay, what is the value of E square? So 1.602 into 10 to the power minus 19 square. Okay, multiplied by 0.419. So how much you are getting? Just calculate and let me know how much you are getting. You all are attending the lecture from home, so you can bring your calculator if you have, and practice the calculation. Yes, calculate and tell me 1.602 into 10 to the power.
I'm getting a very high value.
Okay. How much you are getting?
25,714.
260.
260 you are getting, right? Okay,
Yes, sir.
260 you are getting. But unit? So unit you are not getting, right? Okay. So, okay, this is true, not exactly, I cannot say this is wrong, but we will have to see here things that, what is the exact formula here? Okay. 5b, just to check here, let us talk about here, K, T, ln, Na by Ni, right? This is true. This is the formula. So now we will check the formula, check everything. So root under 8.85 into 10 to the power minus 12 into 11.7, or if you don't want to convert, then you can simply here write 10 to the power 14 farad per centimeter, so that we will not convert the doping concentration in per meter. 10 to the power 14, yes, here 10 to the power 17 now. So it will be 1.602 into 10 to the power minus 19 square, and the value of kh, now we don't need to convert it into the electron volt. So simply we will have to put the value of Boltzmann constant. So if you have calculator, then you can directly get the value, that is 1.38 into 10 to the power minus 23 multiplied by ln 10 to the power 17 by 10 to the power 10. So now you can calculate the value now once again. So what is the value you are getting? 2 into root under 8.85 into 10 to the power minus 14. Okay, calculate now. Yes. KT, T means we will have to multiply here 300. Okay, sorry. Okay, 300. Yes, how much you are getting?
260.04.
Still you are getting the same value. Still you are getting the same value? No, it will be 1.0379 into 10 to the power minus 5 centimeter, because all the values in centimeter, right? Please recheck the value. You need to recheck now. You will get 1.3067 into 10 to the power minus 5 centimeter. Yes. Calculate. Otherwise, you will not face any difficulty in the exam. It will be good if you will practice here.
Yes, sir. 1.039 into the
Good.
average population.
Good. So it is in centimeter, right? Centimeter means it's a very big quantity for devices, right? Because we usually the length or width of the device is in either in micrometer or nanometer. So we will convert this unit centimeter to the nanometer. So just convert, if you will convert from centimeter to nanometer, then in that case, that is 1 centimeter, which is equal to 10 to the power 7 nanometer, right? So this is the 1 centimeter is equal to 10 to the power 7 nanometer. So it means that our result is almost 103.79 nanometer. This is the width of depletion layer. Any doubt here? Yes? You can, if you have doubt, then you can tell me. 1 centimeter is equal to 100 10 to the power 7 nanometer. Then if you will convert 1.0379, then you will get this much value. Okay, so if you are not getting the conversion, that let us say, so 1.0379 into 10 to the power minus 5 centimeter, we know very well this is equal to how much? 10 to the power 7, because we know the formula. Okay, so how do you convert? Okay, so now next, talk about the inversion layer, that is inversion region. So what is the formula to calculate inversion region? X is equal to root under 2 minus root under 2 minus 1 by root 2 multiplied by Wm, right? So here root under 2 minus 1 by root under 2 multiplied by 100 0.375 or 79 nanometer. So what will be the value here? Now x is equal to, that is inversion layer thickness. Yes. Minus 1 by under root 2. Calculate and tell me the value. 103.79. So what will be the value?
30.4.
Yes. Good. 30, nearly 30.4 nanometer. So now we have to see the impact of doping, right? Impact of doping. That's why I have given the various doping concentration to calculate the depletion region width and inversion layer width for the doping concentration of 10 to the power 18 and 10 to the power 19. So you have to do calculations at home and please tell me the value in the next class. No, so let us talk about the characteristics of MOSFETs today's class. So we are going to discuss the characteristics of MOSFET. And one more thing I would like to say, if you write the value, let us say we are writing the value that is 30.4, and if you do not mention these things, that is unit, then you will get 0 marks. So, if SI unit is missing. So don't forget to mention the unit. So now we are going to talk about the characteristics of MOSFET. Okay. So first characteristic, which is known as input characteristics, or you can say input, or you can say transfer characteristics, or you can say transfer characteristics. And second, so in transfer characteristics or input characteristics, we draw the characteristic that is IV, that is drain current, versus VGS. So what is VGS? Yes?
Gate to source voltage.
Good. Now second, that is output characteristics. Output characteristics. So we draw the output characteristics versus ID versus VDS for several values of VGS, right? So what is VDS here? Yes. What is VGS? VDS. So you don't know. VDS is
Drain to source.
drain to source voltage. So now let us discuss about the transfer characteristics. Transfer characteristics. Do you have any other class after 12?
No, sir.
Okay, so today we will continue and we will finish this topic. Okay, so if you remember the device structure here, so if you remember device structure, right? So here p-type semiconductor, this is n plus, here this is the gate, right? Gate, here will be source, and here this will be drain. So what can you observe from here, right? That gate terminal has been, or you can say there is no electrical contact of gate layer with the bulk semiconductor, or you can say with the source or drain. Do you agree? This layer is the SiO2, that is as an insulator. So what you can observe from this diagram, the gate terminal has no direct contact with the source, drain, and p-type semiconductor, right? Can you observe this?
Yes, sir.
Yes. So what does it mean? It means that the gate current, whenever we talk about the current, we always talk about the drain current. But why do we not talk about the gate current?
Nearly zero.
Why it is zero?
Because there is an insulator in between.
Exactly. Because since the gate terminal is electrically isolated from the remaining terminals, that is drain, source, and bulk. So the gate current is essentially zero. So the gate current is essentially zero, so that the gate current is not a part of the device characteristics. Right? So if I ask you in the multiple choice questions, why the gate current is not a part of the device characteristics, so your answer will be like that: the gate current is electrically isolated from the remaining terminals, that is source, drain, and the bulk. Therefore, the gate current is essentially 0. So gate current, if the gate current is essentially 0, what does it mean about the resistance? What will happen?
Infinite.
Infinite. Very good. Ideally, it will be infinite. Means practically you can say it is very high. So this is the ideal value. However, practically it will be very high. Why I am saying very high? And this is also the ideal value. Always remember, this is the ideal value. However, practically there will be some leakage current, right? So due to that leakage current, whether maybe the current, the range, the value of that leakage current will be in picoampere, or you can say femtoampere, you can say like that. So the resistance, then practically the resistance will be very high. We cannot say that practically the resistance will be infinite. But ideally, whenever we will talk about the ideally, so ideally the gate current will be 0 and resistance will be infinite. So you should know the reason why the gate current is 0. So now you know. Now we will talk about the transfer characteristics. So we know very well here, since this is the N type MOSFET or P type MOSFET. Which type of MOSFET is this?
N type.
N-type.
Oh, good. So N type MOSFET is there. So it means that we have to apply the positive gate voltage or negative gate voltage with respect to source?
Positive.
Positive. Very good. Good. Now you are studying. Really good. It is very good for you all. So now we will draw the input characteristics. Sorry, that is transfer characteristics, you can say. So here we will draw. So for the input characteristics, so the current will be, the device current will be ID, that is drain current, which will be in the milliampere, you can say. Or sometimes you will get the result, that is drain current is microamperes. And here you will vary on the x-axis. What you will vary? VGS, right? VGS, which is in volt. That is gate to source voltage. Okay. So as I told you, if you remember first point here, the ID versus VGS for a small value of VDS. So let us say VGS here. Okay. The small value of VDS. So we are also applying 0.1 volt, 0.2 volt VDS. Okay, so how it will be, how it will vary? So on the here it will be 0. Let us say here 10, 20, 30. Let us say this is 40. Here, let us say here 50. Okay. On the x-axis, let us say this is 0 0.2, 0 0.4, 0 0.6, 0 0.8, and here let us say 1.0. So how the current will flow? We will see here. Okay. So see here how the current will flow. Okay. So the variation of the current will like that. So here you can observe, at this point, right? This point is VTH. Okay, so what can you say that the transfer characteristics curve can locate the gate voltage at which the transistor passes current and lifts the off state. So this is the device threshold voltage. So as you can see from the graph, that everything you can understand from the graph here. So for this voltage range, what is the value of current?
0.
Yes, 0. It means that here the transistor is in off state, right? Off state means the current is 0. It means resistance is high, or you can say infinite, right? So what is happening? However, if the gate voltage reaches this point, then after that you can see that the drain current starts elevating, means it starts increasing, right? So this value is known as the threshold voltage. So after this, beyond this value, what is happening? If you will further increase the gate to source voltage, then the current starts increasing rapidly, right? So if I ask you to write about the characteristics, then what can you say that the transfer characteristics curve can locate the, what do you mean by, first of all you should know what do you mean by the transfer characteristics. So the transfer characteristics curve can locate the gate voltage at which the transistor passes current and leaves the off state. So this is the device threshold voltage, and exactly this characteristic is showing like that. So if you will simulate the structure using console physics, Silvaco, or any other or other ticket software, then what you will get to know that whenever you will vary the VGS, so for this range of VGS, that is 0 to, yes, let us say 0.5. So for the VGS from 0 to 0.5 volt, the current is almost 0. However, once we are getting this much value, that is 0.5 volt or greater than 0.5 volt, the drain current starts increasing, right? So it means that the transistor is in on state. So the transistor are in their non-saturated. Here, what is happening exactly? Whenever you will vary the VGS, it will keep on increasing. So keep on increasing means we are not getting the constant value of ID here. It will keep on increasing, right, with VGS. So it means that the transistor are in their non-saturated bias states. So as the VGS increases, VGS means gate to source voltage increases, the threshold voltage is reached where the drain current elevates, right? So what is happening whenever the VGS increases, the ID also increases, right? When it is happening, when the VGS is greater than or equal to VTH. So this point is known as threshold voltage. Okay, so for the VGS between, if you see here, for the VGS between, that is 0, VGS between 0 volt to 0.5 volt, the ID is nearly 0. What you can conclude? ID is nearly 0. It means that, indicating that the equivalent resistance, indicating what? Indicating that the equivalent resistance, between the drain and source terminals, drain and source terminals are is extremely high, right? But what happens? But once the VGS reaches 0.5 volt, right? The current, that is ID, increases rapidly, right? Rapidly with VGS. So what does it indicate? Indicating that, yes, you can tell me the statement now. Indicating that the equivalent resistance, at the drain decreases with increasing VGS, that is gate to source voltage. So any doubt in understanding the transfer characteristics? Yes.
No, sir.
So you need to understand what is the transfer characteristics, what is input output characteristics, so that you people may understand. Now we will discuss about the output characteristics, which is also very much important. So we have already studied about it in brief in the last lecture, but now we will see it in detail. That is output characteristics. Okay. So output characteristics. So here it will be ID versus VDS for different VGS. Okay, so first let us draw the characteristics so that you people can understand what happens in case of the output characteristics. So again here it will be ID, that is it is in milliampere, or here we will vary the VDS, it is in volt. So let us say here 0, 10, 20 milliampere, 30, 40, 50 and so on. Let us say this is 60. Okay, so here the value will be, let us see, so we will draw the characteristics here. So again we are changing the color so that we can understand. See here, if you remember the characteristics of last class, then it will be like that. Okay, so what happens here, just you have to observe the things, not exactly this one. Okay, so see here, so what is happening here, you can see clearly that after this point, let us say this is for, okay, here what will happen, VGS is less than VTH. So here let us say VGS is equal to 1 volt. Here let us say VGS is equal to 3 volt. Let us say VGS is equal to 5 volt. And let us say here VGS is equal to 7 volt. Okay, so what is happening, you have to observe closely. For this particular point of VDS, what is happening, the current tends to saturate. For VGS 3 volt, here you can see for particular this range, what is happening here, the current ID is increasing, but beyond this value of VDS, the current tends to saturate. So this indicates that pinch of locus. So why it is happening? Why the current tends to saturate? I have already explained the reason behind it. So anyone can explain what is the reason that the pinch off occurs and the current tends to saturate? Yes. Yes. I'm expecting
The
all the
width of the channel gets very small.
channel. Yes, yes, you are almost right. You can say
The width of the channel gets very small
width
due
of the
to high
channel
voltage.
at which side?
At that drain side.
Good. Drain side, right? Very small, or you can say there is no contact. It becomes narrow, or you can say negligible at the drain side. So there is no channel, there is no electrical contact. So that's why the current tends to saturate. Now, here you can see for this region, particular this region, what is happening? The current is linearly varying with respect to VDS, right? But for this region, what is happening? The current tends to saturate. Okay, so how applications, they see here, very interesting things from the characteristics. Okay, so here for this region, what you can say, the current is almost zero, right? For VGS less than VTH. So this is known as cutoff region. Okay, so we will talk about the applications. So in case of cutoff region, then it will be very much interesting for you all. So here you can see for the cutoff region, what will be the value of current here? ID is equal to, yes, 0 ampere, right? So it means that the device is, off, right? When there is no current flow from the device, then the device is in off state, right? However, if you see the saturation region, or you can say active region, saturation, or you can say active region, you are getting, yes, what is happening in case of saturation or active region? Yes, just observe the graph and tell
Constant
me.
current.
Constant maximum current you are getting here, right? Here also you are getting the maximum current. Constant, very true, but you are also getting the maximum drain current, right? Agree or not? For the particular value of VGS, here, let us say here, for the particular value of VGS, you are getting the
Yes, sir.
peak current, right? In saturation region. So it means that the device exhibits maximum drain current. So everything you have to observe from the graph, ID max. So it means that the device is in on state. So what you can observe from you can say that as a result, or you can say therefore, that MOSFET or MOS transistor can act as a switch. Why it will act as a switch? Because in the cutoff region the device will be off. However, in the saturation or active region the device will be on, right? So on off means switch. On off is the characteristics of a switch, right? Any difficulty in understanding the first application, that is switch? Yes,
No, sir.
say yes or no. Second point, okay, we will talk about the saturation region. In the saturation or active region, you can also observe that in addition to the maximum current, you are getting with respect to the voltage, with respect to the VDS, that is drain to source voltage, you are getting the constant current, right? Constant drain current. So what will happen here? The device will also act as a constant current source. So this is the second application you can observe. So the device will also act as a constant current source, but in which region? Saturation or active region. Now, let us talk about the third application from the characteristics, that is linear region, or you can say ohmic region. Okay, so just now you will answer. You have to apply your intelligence here. And just let me know what will happen in case of linear region.
Sir, it can
What is
act
happening?
as a
Yes.
act as a register, a variable register.
Yes. Variable register. Why variable register? Because with respect to the drain to source voltage, the current is linearly varying,
Yes.
right? So in the linear region, or you can say ohmic region, the device means here the MOS transistor, the device will act as a variable register. Very good. Okay. So what happens in case of characteristics? So the output characteristics is characterized in three parts. That is, first one is cutoff, second one is linear, and third one is saturation. Right? So one by one we will discuss. That is, let us discuss about the cutoff. Okay. So what happens in cutoff or cutoff region? What is cutoff region? Cutoff region. So the region of the output characteristics where VGS is less than VTH and no current flows. No current flow means ID is nearly equal to 0 ampere, right? So this region is known as the cutoff region, right? So in the characteristics, can you identify where is the cutoff region? This region is the cutoff region, right? Where the VGS is less than VTH, right? Okay, now we will talk about the linear region. Just give me 5 to 10 minutes to explain everything. Okay, so now we will talk about the linear or you can say ohmic region. What happens in case of linear or ohmic region? Okay, so when the channel forms in the NMOS transistor, so when the channel forms, first let me clarify about it, then we will go ahead. So anyone can answer. When the channel forms in N type of semiconductor, N type of MOSFET?
When gate voltage is greater than threshold.
Yes, so positive gate voltage, right? Okay, and which type of channel we form? N type channel or P type channel?
N type.
N type, good, very good. I'm really happy. Now, so let us focus on my statement, whatever I will say. So when the channel forms in the NMOS transistor, a positive drain voltage with respect to source creates a horizontal electric field to the source. Okay, let me repeat it. When the channel forms in the NMOS transistor, a positive drain voltage with respect to the source creates a horizontal electric field moving the electrons towards the drain, forming a positive drain current coming into the transistor. So let us see the structure. Where do we have done the structure? Okay. Basically, what happens? Which type of biasing we connect? If you remember, okay, this type of, right? If you remember, so this is VGS and this is VDS. So VDS is positive, right? Means we apply positive voltage at the drain side and positive voltage at the gate side. So what happens when we apply the positive drain voltage with respect to source? So VDS, here the VDS is grounded. If you see the whole like that, right? So we apply here, we are applying the positive voltage.
Yes, sir.
Yes, hello, can you hear me? Okay, so what happens, sorry for the interruption, because of the internet Wi-Fi was disrupted. Okay, interrupted. So now see here. So what happens in case of the
Yes, sir.
my screen is visible? Oh, okay. So what happens? We apply
Yes,
the
yes, sir.
positive voltage at the drain terminal with respect to source. So here under the strong inversion there will be a channel, right? Here there will be a channel. So channel means that there will be a horizontal electric field moving the electric field, horizontal electric field moving the electrons towards the drain, right? Towards the drain, forming a positive drain current coming into the transistors, right? So the positive current convention is used for the electron and hole current, but in both the cases, electrons are the actual charge carriers. So why we're talking about, since here you can see, this is N plus, this is N plus, and channel is also N plus. So what will be the majority charge carriers here? Okay, so listen, whenever we talk about the device, always talk about the device. In case of device, current is due to both means electrons and holes, right? Current is due to both electron and holes. But in our device, that is in case of MOS transistors, the electrons is the current is only due to the electrons. Why due to the electrons only? Because this is N plus region, this is N plus region, and in the channel also we have only electrons, right? So in case of MOS transistors, the current will be due to the, yes, current will be due to the only yes,
Electrons.
electrons. So say loudly, don't feel shy. If you say wrong, I'm not going to scold you. So it is only due to the electrons. So in case of the MOS transistor, the drain current is only due to the electrons. That's why we call it as a unipolar device. If you have attended the first lecture, then you have remembered the term that is bipolar transistor and unipolar transistor. So this is the main difference, and this is the explanation of unipolar devices. Because in case of unipolar devices, the current, that is the ID current, drain current is only due to the electrons for the NMOS transistors. However, for P-type transistors, the
Holes.
drain current is only due to the holes. However, if you talk about the BJT, that is bipolar junction transistors, in that devices, the current is due to both, that is electrons and holes. As a result, in case of BJT, the noise are the major concern. However, in case of unipolar devices, that is, for example, for instance, you can say MOSFET, the noise are very less. Okay, so what happened if the channel, so here, if you see, the direction of this field is horizontal, right? Horizontal means this one, or vertical you can say this one, or vertical you can say this one. This is the horizontal. Horizontal, and this is the vertical. So between the source and drain, right? So if you will apply the positive terminal, positive battery, or positive potential at the drain, then there will be a horizontal field between the source and drain. But at the same time, you are also applying the gate voltage or the positive gate voltage at the gate terminal, then there will be a, what will happen? There will be a vertical field, right? Because you are applying the voltage from the top side. Any doubt here?
No, sir.
Okay. Any difficulty in understanding the direction of the field? The channel, that is horizontal electric field, is of the same order, or you can say smaller than the vertical thin oxide field. Thin oxide field means the field is generating from the gate side, right? This one. So if the order, you can say magnitude of the horizontal electric field is of the same order, or you can say less than the order of the vertical field, then what will happen in that case? Then the inversion channel remains almost constant through almost constant, or you can say uniform, along the device length. So this is known as the device length. So the length between, or you can say the distance between source and drain is known as the channel length of the MOS transistors. Once again, I am repeating, the distance between the source and drain is known as the channel width. So when the inversion channel, or you can say the remains constant or uniform, whenever the magnitude of the horizontal electric field generated with the application of positive voltage at the drain side should be of the same order, or you can say less than the vertical thin oxide field, then in that case only the inversion channel remains almost same uniform along the device length. So this continuous carrier profile from the drain to source puts the transistor in a bias state that is called equivalently called either the non-saturated, linear, or ohmic bias state. Okay, so maybe you will be confusing here. So what happens in case of linear or ohmic region here? So here you can say that the first point, you can say the inversion layer, or you can say region age, almost age, okay, you can say remains constant, or you can say uniform along the device length, along the device length. But the question is why it is uniform or why it is constant along the device length. So why? Yes, why?
So, in this point, is this equivalent to saying that there will be no pinch off? Is that
There will
what the
no,
point
yeah,
is
there will be no pinch off. Yes, in the linear region there is no pinch off.
That's what this point is saying, right?
Yes, there will be no pinch off because the inversion layer, or you can say inversion region, remains same along the device length. But my question is why it is uniform? I have already explained. Because here the horizontal answer is horizontal electric field magnitude of, you can say, order of horizontal electric field generated by the positive applied bias at the drain terminal is same, or you can say quite less or smaller than the vertical thin oxide film. So we have already understood the horizontal and vertical field. Okay, so this is the region. So the order of the horizontal electric field generated by the positive. So horizontal, what is the direction? Horizontal electric field means from source to drain, right? And vertical field is from the surface of the, from the gate terminal to the surface of the device. Okay, so what happens? So because of this, what happens? So the continuous carrier profile. So continuous carrier profile means if the width or region, here you can see it is constant, right? Here it is uniform or constant along the source and drain. So the concentration of electrons in the channels will be, yes, continuous, right? Means same throughout the length of the channel. So now here, okay, so mathematically you can also understand here. So in this state, what will happen? So if you see the diagram or you can see the device structure, then you can conclude that here, because of the channel, because of the inversion layer, the drain and source of the device are short circuited, right? If there is no channel, then in that case, what will happen? The source and drain will not be short circuited because of the p-type carriers here, right, in the channel. But once the inversion layer forms, then there will be a formation of channel between the source and drain. As a result, both the source and drain terminals will be short circuited. Do you agree with this statement? Right? Yes. Speak up, please. If the channel has been formed, it means that the source and drain terminals are short circuited. Okay, now what happens in case of this? The drain and source are short circuited. So this happens when VGS, that is gate to source voltage, is greater than VDS plus VTH. This is the condition, right? So under this condition, what happens? Drain current is linearly related to the drain to source voltage, that is VDS, over small intervals in the linear bias state. But what happens if you will further increase the VDS? Let us, because VGS is always constant for particular value of VGS, we get the output characteristics, right? So if we will increase further the VDS, then what will happen to these equations? Can you guess? If you will keep on increasing the VDS, then what will happen to these equations? Yes? Can you guess? Yes. Hello? Can you hear me? I've already left the class.
Yes, sir.
So what will happen if you will keep on increasing the VDS? Then what will happen to these equations? If you will keep on increasing the VDS to these equations, it means that the VDS, if let us say, if you will keep on increasing, if you will keep increasing VDS, right? If you don't understand, then I am here to explain. Then what will happen, VDS, then the above equations, that is VGS will be less than VDS plus VTH, right? So what will happen in that case? In that case, then electric field, that is horizontal electric field, becomes stronger, than the thin oxide vertical field, right? Vertical field at the drain side, right? So at the drain end, you can say. So what will happen? Creating creating a asymmetry of the channel. Of the channel carrier inversion distribution. Inversion distribution. So what will be the diagram now? How you will understand the inversion, asymmetry of the inversion. So see here the diagram. This is n plus, this is n plus, this is p. So what will happen in case of if you will keep on increasing? So this is the channel, right? So channel. So what is happening here? See here. Here the width of the inversion layer from the, this is source side, this is drain. So you can see for the source side, the width of the channel is very large. However, if you can see at the drain side, it is almost negligible. So why it is negligible? Because whenever you will further increase the drain voltage, the magnitude of horizontal electric field becomes stronger than the thin oxide vertical field at the drain side, creating a asymmetry of the channel carrier inversion distribution. Right? So for this, at this point, what will happen? The drain current will tends to saturate for the further increase in drain to source voltage for a fixed value of gate to source voltage. Right? So just give me 2 minutes here to explain about the saturation region. Saturation region. So let me check how many people are present in the class now. Oh, only 52. Wow. Okay. So what happens if the drain voltage rises or increases while the gate voltage remains same? Because what happens in case of output characteristics? We vary the drain to source voltage. However, we keep the gate to source voltage, that is VGS, constant, right? So if the drain voltage increases while the gate voltage remains the same, then the VDS, then the VGD, that is get to drain voltage, what happens can below the threshold voltage. So what will happen? See here from the this point here, whenever you will increase the VDS while VGS remains the same, then at that time get to drain voltage, that is VGD, can be less than, you can say, V threshold voltage, right? Then what happens? So what will happen in that case in the drain region, in the drain region? So what will happen? There is no carrier inversion at the drain. As a result, there is no carrier inversion, at the drain gate oxide region. So what will happen? So the inverted portion, so the inverted portion of the channel retracts from the drain. Retracts means removed from the drain, and no longer touches the drain terminal. Okay, touches the drain terminal. So it means that So if you see the diagram here, then you can understand. Here you can see what is happening here. It becomes so much narrow that it is unable to touch the drain side. It means that there will be no longer flow of carriers from source to drain. So as a result, what will happen? The current will tend to saturate. Right? So what will happen? Touches this terminal, means drain terminal. So that there will be a pinched off portion. So the pinched off portion of the channel forms a channel. Okay, so you can also understand here. So since this is the asymmetry of the of the inversion layer, so here you can see that if you see here, then in this region the depletion region is higher, right? The depletion region is higher in this case. In case of pinched off case, the depletion region is greater at drain side due to pinched. What will happen in case of source side? Yes, it will be less, right? The width of depletion layer will be less, right? True? Are you able to understand this concept? Yes.
Yes, sir.
Okay. So what will happen? So the pinched off portion of a channel forms a depletion region, region with a high electric field, higher electric field just below or to the surface of the drain side, or you can say at the drain side. Electric field at the drain side. Right? So what will happen? The end drain. So the drain is n plus, right? So it means the end drain, as a result, what will happen? The end drain and p-type bulk forms n plus p junction, right? If you see the diagram here, see here, this is n plus, this is p. So at the drain side, there will be a formation of n plus p junction diode. Okay, so when this happens, the inversion channel is said to be pinched off, and the device is in the saturation region, right? So in that case, the voltage that is okay. So we will see. Okay. So what happens here? In this case, the VDS is greater than VGS minus VTH. Why it is happening? Because we know very well the equations, as you remember earlier, I write VGS is less than VDS plus VTH. So if you rewrite these equations, then VGS minus VTH greater than VDS. So this is under saturation. However, in case of linear, what is the range? VGS is greater than VDS plus VTS. So you have to remember linear region. Now, 1 minute, just only one thing. Mathematically, how can we represent the current equations with the okay, mathematically? Just 1 minute, mathematically. The characteristics, how can you define the characteristics? Just see ID. So in cutoff region, let us divide the cutoff region. So in cutoff region, what is the value of ID? Yes? Just only for the cutoff region, you have to tell me what is the value of cutoff region, current in cutoff region?
0.
0 ampere, right? So here, that is the range will be VGS H less than VTH. Now we will talk about the linear region. So mu n epsilon oxide T ox W by L within the bracket VGS minus VTH multiplied by VDS minus VDS square by 2. This is for the ohmic state. Ohmic state means linear region, right? Okay. So now saturation region, mu n, okay, wait. I will let you know what is mu n. Mu n ox by T ox W by L within the bracket VGS minus VTH square. So this is in the saturation region.
So I
Or
think it
saturation
should be
state.
VGS minus VTH square by 2.
Sorry?
So VGS minus VTH whole square by 2.
Whole square by
I
2.
think. Yes.
From where did you get to know that?
Sir, we will put VDS is equal to VGS minus VTH in the ohmic state equation.
Here.
Yes, sir.
So it is already by 2. VDS square by 2 only. Not whole.
Yeah, we will put VDS is equal to VGS minus VTH in this equation.
Okay. So see here. Here what is mu n? This is the mobility. Mu n means electron mobility. What is epsilon ox? This is the permittivity of oxide layer. Of oxide layer. And T ox is the thickness of oxide layer. Thickness of oxide layer. And what is the W? This is the width of the device. I will let you know what is this. And L is the channel length. Channel length. Okay. So channel length we know very well. The distance between source and drain is known as the channel length. Width. So if you see our device structure, so let us talk about this structure. Where is it? This one. So this is 2D diagram. 2D diagram means this represents only the x and y coordinate. But we are not drawing it. We are not drawing this structure. It is in 3D, three-dimensional. So whenever you talk about the three-dimensional, then there is one quantity which is known as the depth, which is in the z direction, right? So the W represents the width of that device. It is in the z direction. So this is all about today's lecture. If you have any doubt, then you may ask right now. In the next lecture, we will solve some numericals based on the mathematical equations for the drain current in linear or saturation states. Don't leave the class immediately. I am teaching for you all.